Hi, I'm Zor. Welcome to Unizor Education. Today we will talk about the third Kepler's law. The first one, if you remember, was that all the planets are rotating around the Sun on elliptical orbits. Then the second law, second Kepler's law, which is, by the way, very important for this particular lecture, was that it actually expresses the area which is swiped by the radius vector from Sun to the planet during the same interval of time. The area which is swept by this radius vector would be the same. Well, today is the third one. Now I will use a lot of information which I have presented in previous lectures, not only the Kepler 1 and Kepler 2 laws, but also I have lecture about ellipse geometry, the planet orbit geometry, and I will definitely use the formulas which I have derived during those lectures. So I do suggest you to actually familiarize yourself with all the lectures related to all the different aspects of planets rotating around the Sun. It's like 4 or 5 lectures which precede this one. Okay, now this lecture is part of the course called Physics Plus for All. It's presented on Unizor.com, and I do suggest you to watch this lecture from Unizor.com, because not only you can watch the lecture, but also you can read the notes for the lecture, which actually is a piece of a textbook. So consider you have the piece of textbook which is exactly the same as the lecture, and you have 2 different kind of ways to absorb the material. In some cases my notes are a little bit more detailed than the lecture itself, primarily because maybe it's kind of boring to go through certain calculations and formula transformations. So I leave it to the notes basically, and I write the result on the board, basically referring you to view the notes if you are interested, or derive it yourself. Also the website Unizor.com contains other courses like Math for Teens, Physics for Teens, Math Plus for All, like this Physics Plus for All. Then there is the Relativity for All, and there are some other things which might be interesting. Okay, so back to business. Kepler's third law. Now, the Kepler's third law states that the period of circulating the planet around the Sun squared is proportional to cube of the semi-major axis of the ellipse of the orbit. But what's important is that the coefficient of proportionality is the same for all planets. So if you will have the period, let's say, of Earth square divided by semi-major axis cube of the Earth, and then you will take the same kind of ratio for Jupiter. Again, the period of rotation around the Sun, which is 1 year, 1 Jupiter year, squared divided by the cube of the orbit's semi-major axis of Jupiter, you will have exactly the same number. It's quite remarkable, actually. But again, it all follows from the laws of physics which we know. And what's interesting is that the Kepler was able to actually derive this from experiments. So he did not have all these the laws of Newton, the second law of Newton, the universal law of gravitation of Newton, and he certainly didn't know all the mathematical apparatus which we are using right now. So it was purely from observation, and it took him years, which is quite remarkable actually, but he still was able to find this particular relationship, and he really admired the result. some kind of a beauty in the way how the nature works. Okay, so let's go from natural beauty to beauty of physics and mathematics. But the first I would like to consider a simpler case of a circular orbit. So not elliptical like real orbits are, but strictly circular orbit with uniform motion around the source of gravity. Let's call it sun in this particular case. So we're talking about planet around the sun, and we consider the planet to be on the circular orbit uniformly rotating. So uniformly rotating, it means you have angular speed omega, which is, well, number of radians per second, let's say. So it's uniform, it's a constant. And you have radius of the orbit. Now you also have T, capital T is the period. So it's one circle around. So the third Kepler's law in this particular case says T squared divided by R cubed is equal to 4p squared divided by g times m, where m is mass of sun, or any central source of gravitation, which is fixed in space, and g is a gravitational constant. So basically everything depends, only the variable here is sun, which means for all planets of the solar system, this ratio is exactly the same, so this ratio is exactly the same. So if we have a radius, but again, that's considering all the planets are on circular orbits. Doesn't really matter how far it is, but the farther they are, the period will be greater, and the ratio of T squared by R cubed would be the same. So that's my purpose. Okay, so how can I prove it in case of circular motion? Well, it's actually quite simple, because the centripetal acceleration A of the body of object or planet, which is which goes around some kind of a source of gravitational field, is equal to R times omega squared. Now, how can I basically derive this? Well, again, if you're interested, very quickly, position of the object which is circulating the central gravitational source can be described by vector r, which depends actually of time, and it contains two components, x component, which is r cosine omega t, and y component r sine omega t. So that's basically the x and y coordinates when the object is circulating on an orbit. So this is angle. Now if the time from here to here is t and angular speed is omega, so this angle is omega t. And if this is my object, now this is x coordinate, which is r times cosine, and this is r times sine, the y object. Now from this we can derive vectors of speed and acceleration. So the speed vector, which is the first derivative, would be equal to x coordinate would be what? R is a constant, omega is a constant. The derivative of cosine is minus sine times derivative of inner function, which is omega t, which is omega. So it would be minus r omega sine omega t, and here derivative of sine is a cosine, so it would be r omega cosine omega t. So this is my vector of velocity. Now vector of acceleration would have the second derivative, so it would be minus r omega squared cosine omega t minus r omega squared sine omega t. So that's my vector of acceleration, and its magnitude, which I call r, would be square root of r square omega square cosine square omega t plus r square omega omega to the fourth, I'm sorry. Omega to the fourth sine square omega t cosine square plus sine square is 1, so we have square root of r square omega 4, so it's r omega square, which is I wrote. Okay, so this is a very quick derivation. Let's forget about this. It's simple. Now, okay. So, if I know the acceleration, I can use the second law of Newton, which is F is equal to ma, and the universal gravitation law, which is the same force F, is equal to g m divided by r squared, right? So this is mass of the central source of gravitation, mass of sun, this is mass of the planet. From here I can do obviously this, so A is equal to gm divided by r squared on one hand. On another hand, it's equal to r omega square. So omega square is equal to gm divided by r cube, right? Okay, now what is omega? Omega is angular speed. If you have a period t, so during the period t there is a full circle, so it's 2 pi radian divided by t. So omega square is equal to 4 pi square t square, right? I square this. And as a result, t squared divided by r cubed is equal to 4p squared divided by gm, which I wanted to prove. So in the case of a circular motion, that's kind of easy, and you don't need much theory except just regular manipulation with coordinates. Now, in case of elliptical orbit, the situation is a little bit more difficult, but all the complexity have already been addressed before in the previous lectures. So I will use the results of the previous lectures, and again, if you did not really watch these lectures, you can always return back, go to unizor.com, return and go to previous lectures to basically make sure that you understand why exactly I have used certain formulas. Okay, so for elliptical orbits, let's use, first of all, let's start with second Kepler's law. Now, the second Kepler's law tells me that if this is the ellipse of rotation, now this is sun, which is one of the focal points. So if you will take two positions, one position at T1 and another at T2, and you have the area which the radius vector from sun to a planet swept as part of this orbit, then this area, let's introduce function a of t, which is basically a of t, this is t, and this is t is equal to 0. So from 0 to some t, this is the area. So this area is actually equal to, and I will use the formula which had been derived in the lecture for the second Kepler's law. Now this formula is 1/2 L t divided by m. T, not this t, this t. It's proportional. So basically, the derivation of this was the following: d by dt is equal to this. So that was my result in the second Kepler's law, and this obviously derived from this particular property that the area swept from one interval to another interval depends only on the time difference and not on a particular position anyway. And from this, obviously, you have as the following: this is the first derivative is equal to constant. This is the constant, so you have to just multiply it by t. Now, why is this constant? Well, this L is angular momentum, and again, during the movement in the gravitational field, it's a central field. In the central field, angular momentum L, which is m times position times velocity vectors, and this is the cross product, vector product. So this is constant. Again, it was proven before in one of the lectures, and you can always refer there. So if this is the constant, then this is the constant, the first derivative, so the function itself, you have to just multiply by t, because the value of a of 0, obviously it's 0, because we started from the moment t equals 0. Okay, this is one of the things which is, again, was addressed before, and I will use it. Now, so that's the first thing. Now, on the second thing is, if I will have, instead of this, not as a function, but function at specific moment, t, capital T, which is a period. Now, what does it mean that it's a period? It means its area during, which is swept by the vector during the whole cycle of movement of the planet around the sun. So it's the area of this ellipse, basically, right? And again, the area of the ellipse, we know what it is. And again, it was addressed in one of the lectures before. That's pi AB, where A is semi-major axis and B is semi-minor axis. So this is 2A and this is 2B. So semi-major is this piece, semi-minor is this piece. Now this is a focus and this is another focus. Okay. So I will use this formula. So basically I have so this is T. Okay. So I have the relationship between semi-major and period of rotation, but that's not exactly what I wanted yet, because there are mass here, there is a angular momentum, there is a semi-minor, so it's not really what I want. So, but gradually I will come from here to what I would like to have. I would like to have t squared divided by a cube is equal to 4 pi squared divided by gm. That's what I want. Now, where a is, it's not an acceleration as before, centripetal. No, this is the semi-major axis. Okay, so that makes sense. So I would like to come up with this formula from this. Well, quite frankly, it's just technicality. I'm just using the formula which has been derived before, transform them, and I will get this one. So just follow me as far as you can. Okay, so starting from this. Now, this is a constant, which means if I will choose an initial moment of time, this one, and I will have position r0, which is a basically different distance from sun to a planet at its furthest point on the orbit, which is called aphelion, and this is velocity v0, which is in this case perpendicular. and since it's perpendicular, their vector product is basically equal to their the value of vector L is equal to the value of this, and value of this in this case is equal to multiplication by their magnitudes. You see, these are vectors, these are magnitude of these vectors. So this is just the distance r0 from Sun to the furthest point, which is aphelion, and v0 is just the magnitude of velocity, which is speed. And these are, we can consider them as being given, although at the very end they will all cancel out anyway. Okay, so I will just use this particular expression, in which case if I will put it here, I will have that 1/2. Now instead of L, I will put this, and I will cancel M, so I will have R0 V0 T. Am I right? 1/2 L divided by M, which is R0 T, and this is equal to pi A B. Okay, so this is basically the formula from which I will start. Now, in the in one of the previous lectures, where I was talking about geometry of planet's orbit, I have derived the geometric characteristics of this ellipse, and these are semi-major axis A, its eccentricity, its minor semi-minor axis. So I have derived expressions for all of these based on initial R0 V0, which is the distance and the speed, at the point t is equal to 0. So I have expressions of all these using R0 and V0. And I will just use it, basically. And then I will just put it here, and you will see how everything comes out to a regular, very good expression like that one. So now the semi-major axis was R0 divided by 2 minus beta. Beta is a coefficient which I have artificially choose. It's R0 V0 squared divided by G times M. So that was in that lecture where I was talking about. It's just very convenient to use this particular abbreviation because the formulas will be very easy. Now the eccentricity was 1 minus beta, which is also very easy. The semi-minor was a little bit more involved. It's R0 square root of beta times 2 minus beta divided by 2 minus beta. So it's still not completely ugly expressions. It's relatively fine. But that's basically enough for me to just go through pure technical manipulation. I will just put A and B into this formula, and you will see how everything comes out. So what should we do now? I mean, I don't like to have the square root of here because it's here. Let me just use exactly the same formula, and I'll just square both sides. And I will have that R0 square V0 square T square is equal to 1/2 would be there too, so it would be 4 pi square A square B square. And I will substitute A and B into this thing. So A square is equal to R0 square 2 minus beta square, right? And B square would be equal to R0 square beta, so 2 minus beta divided by, yeah, that's it, without square. And this is square, 2 minus beta square. All right, so substitute it here. So what will I have? 4p squared A square, which is r0 square divided by 2 minus beta square. And b square, which is this, which is r0 square beta 2 minus beta divided by 2 minus beta square. All right. So r0, 2 minus beta, I will have 2 minus beta cube. Okay. Okay. Now beta is r0 v0 square divided by gm, right? Okay. Now v0 square, v0 square. Now this is r squared times r, so I will put it r cube. And what do I have? T square is equal to 4p square r0 cube divided by 2 minus beta cube. Now look at this. A is r0 divided by 2 minus beta. So this is r cube divided by 2 minus beta cube, which means it's equal to 4p square A, and by the way, I forgot gm, divided by gm, A cube, r cube, so it's A cube. So this is A cube, from which t squared divided by A cube equals to 4p squared divided by gm, which was required. But again, everything is based on things which I have already excuse me, derived in other lectures. So basically these are geometric properties based on initial values of position and velocity of the planet at some t is equal to 0, where the planet is furthest. I chose that particular. But to tell you the truth, if I will choose some other point as a beginning, I will have different r0 and v0 as vectors, but the orbit is supposed to be the same. So basically, no matter how I calculate, this is not dependent on initial position. It doesn't depend on r0, v0 in this particular case. So if I start from any other point, it will be the same formula. And again, what's important is that there is absolutely no dependency on the fact that these are different planets. So all planets have their own semi-major axis and the period of rotation. So for all planets, this ratio will be the same, because this is the mass of Sun, which is constant for all planets, and these are constants. So that's something which, again, Kepler was quite amazed about, that take any planet, divide square of a period by a cube of semi-major axis, and he will have exactly the same number. That would be, that was quite remarkable at that time. And what's remarkable here is that you can theoretically derive exactly the same thing. So I suggest you to read the notes for this lecture. They are maybe a little bit more detailed. I did it quite fast, actually. Well, that's it. Thank you and good luck.